Hi students, this is the third main lecture. In the last class we studied relation and types of relation. Reflexive relation, symmetric relation and transitive relation. Let me give one more example. Say Z is the given set of integers and R is a relation in Z defined by set of elements AB such that 3 divides 3 divides A minus B. So show that it is equivalence relation. This is the first thing. That means we can show that the given relation R is equivalence relation, meaning I have to show it is reflexive, then I have to show it is symmetric, then we have to show it is transitive. So first one, R is reflexive. R is reflexive. So now remember the definition. Definition says for every x in Z, xx must be here. So now let x be an element in Z, then x minus x is 0 and this 0 is divisible by 3 or 3 divides 0. So this implies x belongs to R. So by definition therefore R is reflexive. So the first thing is established. Second, R is symmetric. So we can prove like this. The definition of symmetry says whenever xy is in R, I have to show yx is in R. Therefore, suppose xy belongs to R, this implies 3 divides x minus y. If I write like this, this means 3 divides x minus y. So now this implies 3 divides y minus x also, because whenever an integer is divisible by 3, it is also divisible by y minus 3. Sorry, it is also the same number when you take negative, that is also divisible by 3. For example, let me make it clear. Say it is 15. 3 divides 15. 3 divides minus 15 also. So this is again. Therefore, this implies yx belongs to R. This implies R is symmetric. So we proved it is reflexive and symmetric. Then we have to prove transitive. So let us take the next concept. So R is transitive. What is the definition? If xy belongs to R, yz belongs to R, we have to prove xz belongs to R. Let us see how to do it. So transitive. Let xy be in R and yz be in R. This implies here xy belongs to R means 3 divides x minus y. I will use this symbol. 3 divides x minus y and 3 divides y minus z also. This implies 3 divides x minus y plus y minus z also. For example, suppose this is say 9. 3 divides 9. Suppose this is say 12. So 3 divides 12. Then 3 divides 9 plus 12 also. You can check. So this implies here what happens? X and x cancel. 3 divides x minus z also. So this implies xz belongs to R. So xy belongs to R, yz belongs to R, implies xz belongs to R. So R is transitive. Thus it is reflexive, symmetric and transitive. Therefore, it is equivalence relation. Equivalence relation. So this is what we established. But what I want to tell something more is this equivalence relation has a specific property. It's very interesting property that let me tell you. Here you see with the same example. Here you see when you take Z, if AB belongs to Z, the difference of that element is divisible by 3. For example, if I take say 3, I can take 6 also. These two are related. I can take 3 with 9 also. These two are related because difference is divisible by 3. You take any number, I will write here though, that set dash dash, then 0, then 3, then 6, 9, etc. Here this side also you can write minus 3, etc. All these integers, when you take the difference of them, it is divisible by 3. So let me call this as 0 set because 0 is contained here, 0. And then Z1, see this set contains, first element I will write 1 here, then it is 4, then 7, then 10, etc. This side of course you can write. So here also you see 4 minus 1 is 3, divisible by 3, 7 minus 4, or even if you take 7 and 1, 7 minus 1 is 6, 10 if you take 10 minus 1, 9, all are divisible by 3. So this is another set. The third one I can write Z2 equal to same thing 0, 1. Here I will write 2 as first element, then 2, then 5, then 8, then 11, etc. So what I have done is Z is divided into 3 sets, Z0, Z1, Z2. And I can't go further because Z3 is here only. Because Z3 means what? I have to take 3, but 3 is here. So all the numbers are repeated. So this relation actually divides the set Z into 3 subsets. Now these subsets have two properties. One is every element here, of course, that is very clear. Every element here is related to every other element. That is one thing. Second one is if you take this set and this set, no element is repeated. They are disjoint. If you take these two, once again they are disjoint. If you take these two also disjoint. This is the first thing. Second one is if you combine them, that means union of these three, you will get Z. So actually this is the property of any equivalence relation. An equivalence relation divides the set, given set, into subsets satisfying two conditions. First one is all the subsets are mutually disjoint. Second one is when you make the union, that will give you Z. So this is the thing. So this set Z0, Z1, Z2, etc., which are the result of this relation, they are called equivalence classes of sets, classes. That means they are denoted also by 0, then here 1, then here 2. Meaning, if you divide any element here by 3, remainder is 0. If you divide any element by 3, remainder is 1. That means all these numbers are having common characteristic. They all leave the same remainder when divided by 3. And now you can extend this characteristic. Suppose you take 5 here, then what happens, this relation divides classes into 0 equivalence class, 1, then 2, then 3, then 4. So is the thing. So let me generalize and give the idea of this one. So take a set A, and suppose R is an equivalence relation on A, then R is dividing this set into A1, A2 or A0, A1, A2, etc. You can type A1 also here. So A1, A2, AN. But what is the condition? First condition is AI intersection AJ is always pi I not equal to j. This is the first condition. Mutually disjoint subsets. Second one is A1 union A2 union etc. AN. This is Z. This is called, actually we are using a word, partitions. Partitions. Partitions means actually the equivalence relation are partitions the set A into this A1, A2, A3 etc. AN, which are mutually disjoint, and when you take the union it becomes Z. So that is called partition, and this is one of the important properties of equivalence relation. So with this, let me conclude the first section of this chapter 1, that is relation. Of course, as I told you, more and more problems which are there in the exercise, let us work out later under supplementary lesson. Now let me continue with the next concept, that is function. That is function. So this is the thing. This is also not new. We studied this in the last year, second chapter, function, relations and then functions. So let me recall what is function. Function is also a relation from a set A to another set B, satisfying two conditions. First condition is that every element x here should be related to some element y here. So this is the first condition. Second one is y should be unique. Y should be unique. That means x should not go to two elements. So if these two things are satisfied, then it is function. So remember, function is also a relation, but it has two specific conditions: every element, and second one, uniqueness. So let me give a few examples. Say a equal to 1, 2, 3 and b equal to, let us say, x, y, z, t. Then if you write f of 1 equal to x, f of 2 equal to y, f of 3 equal to z, then this is a relation because every element here is related to some element here. The first condition is satisfied. Second condition is y should be unique. So here you see 1 is going to x only. So this is a function. Now even you can use the diagrammatic representation like this. Here it is 1, 2, 3, x, y, z, t. Then 1 is going to x, 2 is going to y, 3 is going to z. Suppose you take here a second case, domain, this a and b are same. Then f of 1 equal to x, f of 2 also equal to x, and f of 3 equal to y, for example. Then it is no more a function because uniqueness is lost. 1 is going to x and 2 is also going to x. Sorry, 1 is going to, I made a confusion. So 1 is going to x, f of 1 is going to y, f of 2 is going to z, f of 3 is going to t, let us say. So uniqueness. So here 1 is going to two elements. It is going to x and it is also going to y. So uniqueness is lost. Therefore this is not a function. Even in diagram also you can use. And another case is, suppose you take f of 1 equal to x, f of 2 equal to y. That's all. That means 3 is left out. So every is violated. Every element is violated. Therefore, under two conditions it cannot be a function. One is, if any element in the first set is left, that is not a function. And second one is, if any two same element is going to two different elements here, then also it is not a function. Then we studied some of the terms last. We were using terms associated with functions. Let us first recollect. See, suppose f is a function from A to B, then this is called domain. Domain. And this set is called codomain. Codomain. And we also used one more concept called range. And then we also used one more concept, image. This is the term, one more term. And another one is pre-image. See, these are the terms associated with function. Let me use the diagram so that it is easy to identify. This is A, this is B, this is F. 1, 2, 3, X, Y, Z, T. 1 is going to X, 2 is going to Y, 3 is going to Z. Then these elements are called image, pre-image, and these elements are called image, and this set is called domain, and this set is codomain, and the subset, this is range. So range is actually a subset of codomain. And you should also remember the difference. In case of relation, domain of the relation need not be the first set, because in case of relation every element need not be related. So domain normally in relation is subset of A, whereas in this one it should be A, not proper subset of A. That's one thing. Second one is here, range, there is no such condition. Range can be a subset of codomain, or sometimes it can be the entire codomain also. So this is the thing. Now in this class, let us study the types of functions. First let me introduce the types of functions which we study this year. First one is one function, one. Second one is onto function. Third one is composite function, composite. Last one is inverse. So these are the 4 types of functions we are studying this year. This is also known as injective function. This is also known as surjective. And if a function is both, that is called bijective function. So these are the different terms we are using, and these 4 are the 4 major types of functions we are studying in this chapter. Now let me take the first type, that is one function. So one function. So what is one function? So before giving the definition, let me make the concept clear. You take a set A, say 1, 2, 3, and take the set B as the codomain, say A, B, C, D. Suppose f of 1, f of 2, f of 3, they are defined by, say, A, 1 is going to A, 2 is going to B, and 3 is going to C. So this is called one function, that's all. Meaning, different elements here should go to different elements here. This is a thing. Because in function, 1 and 2 can go to the same, even then it is a function. But in this case, what happens is, different elements are going to different images. So this is a thing. I think one example is sufficient to understand this concept. Now let me give the definition. Definition is this. A function f from A to B is 1 if distinct elements of A are related to distinct elements of B. So this is the thing. See, these 2 important terms you have to remember. This we can write like this, that is, f of x1 equal to f of x2 implies x1 equal to x2. Now you may wonder, now here in the word I am using distinct elements are going to distinct, but I am taking this one equal here. See, last year in logic, that is mathematical reasoning, we studied this one actually. P, if P then Q is also same as negation Q, negation P. These two are equivalent statements. Here also you have to remember like this. I can, logically I can represent this statement like this. F of x1 equal to f of x2 implies x1 equal to x2, or it is also equal to x1 is not equal to x2. This is Q, negation Q. This implies f of x1 not equal to f of x2. So you see, this is actually very near to the same as this one. Distinct elements are going to distinct images. Or in other words, if the images are same, then the pre-images must be same. Both are same. So this is the thing. And remember, normally we use this as the method of proving given function 1, 1. Therefore, we use this. You can also equivalently use this one, but in most of the cases, proving 1, 1, we use this definition. Now let me take a few examples on 1, 1. Say f is a function from say 1, 2, 3 to x, y, z defined by say f of 1 is x, f of 2 is y, f of 3 is z. Definitely it is 1, 1. Distinct elements are going to distinct. Suppose you take f 1, 2, 3 and x, y, z only, domain and codomain same. F of x equal to 1, f of y also, f of 1 is x and f of 2 is x only, f of 3 is y. Then this is not 1, 1, very simple, clear, because 1 is going to x, 2 is also going to x, so it is not 1, 1. So when the given domain is very simple, that is finite, it is not a challenge. You can check, you can draw the diagram and then you can check. But when the given domain is infinite, you should be careful. Say, let me take a few such examples. F is a function from n to n defined by f of x equal to say x plus 1. Is it 1? So we can check like this actually. See, f of 1 will go to 2, 1 plus 1. F of 2 will go to 3. F of 3 will go to 4. So like this. So f of n will go to n plus 1. Even if you want to draw the diagram, you can draw the diagram like this. 1 is going to 2, 1 is left out here, 2 is going to 3, 3 is going to 4, etc. So definitely this is 1, 1 because different elements here are related to different elements here. Please note, I am just verifying, I am not proving. There are two types of questions. One is determine whether it is 1, 1. One thing. Second one is show that it is 1, 1 or show that it is not 1, 1. That is proof. See, first you should know whether it is 1, 1 or not ourselves. See, that's the first thing. See, normally in mathematics, these are the two types of questions. One is determine whether it is 1, 1. Second one is show that it is 1, 1. Show means proving. So let me take one example where it is not 1, 1. Say f from z to z defined by f of x equal to x square. Then it is not 1, 1. Because if you take f of minus 1, this is minus 1 square, which is 1. And if you take f of 1, this is 1 square, this is also 1. That means minus 1 is going to 1 and 1 also going to 1. So different elements here are going to the same image, so not 1, 1. So in case of infinite set, whenever you want to show that it is not 1, 1, it is sufficient if you take 2 examples. You need not multiply it. Now I will give one more example here only, just by changing n to n. Definition of the function is same, f of x equal to x square. Now is it 1 1? Why I am giving this function? Because sometimes as student, we remember only this much. So in the class, teacher has told f of x equal to x square, it is not 1 1. But if you take this as the domain, it is 1 1, because n does not contain negative integers. So f of 1 will go to 1 only, 1 square 1. F of 2 will go to 2 square, this is 2, 4. So all the elements here, they are going to their square, and no two elements here will go to the same number. So it is 1 1. So with this, let me conclude. What new concept we studied today is in function, I am telling 1 1 function, its definition, and some examples which are very simple. So whenever it is finite set, you verify by taking say some diagram or writing elements, and then you decide. In case of infinite set, you should be careful. In the next class, let us take some more very interesting examples, and then we shall verify whether the given function is 1 1 or not. Then we will also try to prove 1 1. Then we will go to the next concept on to. If you like my lesson, please like the lesson, and if you have not subscribed, then please subscribe my channel and share the link with your friends, so that it will be a motivating factor for me to go further with more enthusiasm. Thank you. Take care.